So remind me, to feel an electric field, what must a particle have? So to feel an electric field, what must a particle have? It must have charge. So you guys might recall, this is the force a charged particle feels in an electric field, but it has to have charge. Now it turns out, we can put an analogous equation here. What must a particle have to feel a magnetic field? Well, it turns out still charged. There's this electromagnetic marriage here. So it's still got to have charge, but it's also got to have velocity. So, and then it will fill the magnetic field, and this would be the force. Now, technically, this would be the maximum of the force. It turns out the V and B here is really a cross product. So we're not going to get too much into what a cross product is, but technically you've got to account for the angle between the velocity of the particle and the magnetic field. Cool, so this is actually the force felt by a moving charged particle in a magnetic field. It's not just enough to have charge, it's actually got to be moving. If it ain't moving, it ain't going to feel anything either. And here's where things are going to get a little bit weird. So let's say I've got a positively charged particle moving off to the right here. So, and I've got a magnetic field also pointing towards the right. So here, velocity of this particle is to the right, magnetic field is to the right. What's the angle of theta? Zero. What's the sign of zero? Zero. So when your velocity and your magnetic field are in the same direction, there is no magnetic force on that charged particle whatsoever. What if I change the direction of my velocity instead and make them exactly anti-parallel? What's the angle between them now? 180. What's the sign of 180? Still zero, and there's no force so operating on this lovely charged particle in this case. So got to have some component perpendicular, and when it's perpendicular, that's when you actually have the maximum force. So let's take this lovely charged particle again. Now let's have its velocity point up now. And here's where the fun begins, right? What rule are we about to get into? Which hand? Right hand rule. Good. It is not the left hand rule. So I helped a student with this several years back, and he had the hardest time and just kept pulling out his left hand. So, and I told him that on test day I was going to put his arm in a sling, and I really almost did. And finally, the week before his exam, he finally started getting it down. But I was really seriously considering really putting his arm in a sling. So, but in this case, it's the right hand rule, and the right hand rule defines the force on a positive charge. Now, it turns out the force, the magnetic field, and your velocity are all going to be mutually orthogonal. What does mutually orthogonal mean here? Yeah, they're all in perpendicular planes here, when we are at a maximum anyways. So in this case, velocity and magnetic field, they don't have to be perfectly perpendicular, but the force will always be perpendicular to both of these. So whatever plane these two form, the force will always be perpendicular. So in this case, these two are in the plane of the board. That means the force is either coming out of the board or going into the board. Those are my options. Cool. So notice if the velocity had been off at an angle like this instead, so these two still would have been in the plane of the board, and my force would still be out of the board or into the board, as the case may be. So I'm going to teach you a right-hand rule. For this, unfortunately, there are a number of right-hand rules. There are some where you just keep your hand out straight and point your fingers and your thumbs and stuff in the various directions. That's what I'm going to teach you. There are some where they got the gun and stuff like that. There's some where you cock the gun, and I'm not going to go there. I'm going to keep it simple, but I apologize if you've seen a different one. If you've got a right-hand rule down, great. But we're going to go through 3 or 4 right-hand rules today. So I'm going to try and keep them all consistent here. So we've got a magnetic field. That's where your fingers are going to point. Your velocity is going to be your thumb. And then out your palm is going to be the force. So in this case, we're going to line up our fingers with the magnetic field. We're going to get our thumb in the direction of the velocity, and out our palm is where the force is. So where's the force on this charged particle here? Into the board. This is weird, right? Because if I had an electric field pointing to the right on a positive charge, where would the force be? Still to the right, the same direction. It doesn't work that way with a magnetic field. Also note, if I had an electric field pointing to the right for a negative charge, where would the force be? No, Again, electric field, pointing to the right. For a negative charge, where would the force be? To the left, opposite. So electric field, we had to define, one set of rules for the positive charge and the opposite for the negative. It works the same way with the magnetic here. So in this case, our right-hand rule tells us, again, fingers in the direction of the magnetic field, thumb in the direction of velocity, the force comes out the palm is into the board. If this were a negative charge, it would be out of the board, the exact opposite. Now, one thing to note, if this were a negative charge, I could use a left-handed rule. Fingers in the direction, thumb in the velocity, and coming out would be this. And I would highly recommend you don't do that, because I don't want you to use your left hand on accident in the wrong scenario. So just use the right-hand rule. If it's a positive charge, it comes out your palm. If it's a negative charge, the force comes out the other side. Cool?
So would that be a question if you're looking at it from the paper's perspective or from the magnetic field's perspective?
So it would what be the question exactly?
Like, are you looking at it in the perspective of this? You're the P, and then you're going straight.
Well, I'm just lining my fingers up with the field, the magnetic field, the thumb in the direction of the velocity, and the force comes out my palm into the board. So, whereas if it was a negative charge, the force would come out the back of my hand instead, out of the board in this case. So, but notice it's not about perspective in this case. It's about just lining up your hand, in the correct ways here. So, and this is, I kind of go this way, but notice they're all mutually orthogonal, at least force will be mutually orthogonal to these two. So you could really define this in any of these, three combinations you want to. This is the most common one I've seen. If you notice, if you've done the kind of the gun like this sort of thing, you got your thumb as the velocity, finger is the magnetic field, and this guy is your force, which would be the same thing as coming out your palm. So it's the same right-hand rule in that case. But technically, I could switch and mix and match these in a variety of ways, and I've seen it done a variety of ways. This is the only one I'll do, and every right-hand rule I will try to make look as similar to this as I can for the other right-hand rules we'll learn. Cool? So question number 1, we've got a positive charge, it's got a velocity pointing to the right, and it's about to encounter a magnetic field. When you see a bunch of X's like this, what is this supposed to symbolize? Magnetic field's going into the board. What would it look like for a magnetic field going out of the board? So it's actually just part of the actual pedagogy in magnetism here, is that when you see these X's, it implies there's a magnetic field going into the board. So if you notice, we're going to draw a bunch of two-dimensional diagrams, but we got to deal with 3 dimensions in every single case with magnetism here. And so we now have to define what into the board and out of the board looks like. Into the board is X's. What does out of the board look like? Yeah, you might see a bunch of dots, or you might see a bunch of circles around the dots. Same diff. Whether you see just the dots or the circles around the dots, that means out of the board. So you'll see both conventions. Cool. So in this example, so your magnetic field points into the board. Your velocity points to the right here. So, and the question is a couple things. So when this positive charge in the diagram below enters this magnetic field, it permanently starts moving in a repeating circular pattern. And the question is the motion clockwise or counterclockwise? So in this case, what direction is the initial force it feels? So thumb this way, magnetic field, so this way, and the force it feels is indeed up. And so all of a sudden this thing's going to feel an upward force, which is going to change the direction it's moving. But as soon as it changes its direction, so does its right-hand rule. And it keeps changing around in circles, and you end up with a potential, as long as this magnetic field is big enough, let's extend it out a little bit so I can make a big enough circle. But this thing has a chance of entering this field and just starting to do circles. And so in this case, based on the direction we saw the force, is this clockwise or counterclockwise from our perspective? Counterclockwise. Cool. And the idea is that because your direction of your velocity is changing as the force is applied, then your right-hand rule is changing. You're changing the direction of your thumb. So, and that changes the direction your palm is coming out in the force. But the force is always going to point towards the center of the circle. And if that force is always pointing towards the center of the circle, what kind of force does that really mean it is? It's a centripetal force. Cool. All right, so that was the first half of that question. Second half is now the calculation part, and it says, if the magnitude of the magnetic field is 200 Tesla and the particle has a charge of 1 times 10 to the minus 6 coulombs, and the magnitude of its velocity is 1,500 meters per second, what is the magnitude of the magnetic force acting on it? And that's exactly what this equation is for. What's our theta in this case? 90, and what's sine of 90? 1. So this term will just kind of drop off since their velocity and magnetic field are perpendicular. So how big is this force? Yeah, 0.3 what? Yeah, it's a force of 0.3 newtons. Awesome.
Can you explain the graph part again?
So in terms of just the direction of its movement and stuff like that. So in this case, we started off and our magnetic field points into the board the whole time. That's never going to change. But our thumb initially points off to the right. So where's the force point? Up. And that's why it starts changing the trajectory, because there's going to be a force and a net acceleration upward. But notice as we go around the circle, because now its velocity points up, so my thumb points up, where's the force now? To the left. So then it turns left, and now where's the force point? Down. It just keeps doing circles. Well, because the force always points toward the center. So think about it this way. When I swing a yo-yo around in a circle, why does it keep going in a circle? Because there's a tension in the string pulling it in. So when there's a satellite going around the Earth in orbit, why does it keep going around and around in orbit? Because there's always a force pointing towards the center, gravity. Same thing here. Now, there's always a force pointing towards the center of that circle, which happens to be a magnetic force. But in all three cases, we had a centripetal force pointing towards the center of the circular motion.
So why didn't you choose it just on that area? Could it be any area?
So, well, here's where it entered the magnetic field, and that's where it's going to start feeling that force. And stuff like that. And again, I could have had this doing bigger circles and stuff like that, but it was always going to enter the field right at this point where I kind of showed it.
Okay, cool. Thank you.
Cool. So if I wanted to find the radius of this circular motion, what would I do?
Centripetal force, so mv squared over r.
Yeah, I would set this equal to my centripetal force. It's responsible for it, so the sum of the forces in the radial direction equals mv squared over r. It's the only force in the radial direction, so it equals mv squared over r. Cool, and I just solved for that radius. Cool, wasn't the question in this case, but just another application of the centripetal motion we learned last semester.